Good morning. This is Power Electronics 353. This is, I guess, our fourth week of classes, if I'm right. So this would be our session number 7. We are covering chapter 4 of the textbook, which is covering full wave rectifiers. Do we have any questions before we start? All right, no questions. Okay, so let's kind of review what we did last time. We looked at full wave rectifiers. One of the structures would be a structure that you have on the screen. We are going to use 4 diodes to form a bridge to basically rectify the input voltage waveform. In this particular case, the load is a purely resistive load, so everything is quite simple and straightforward. As it turns out, the output voltage is the absolute value of the input voltage. When the input voltage is positive, D1 and D2 are conducting. And when the input voltage is negative during the second cycle, the second half of the cycle, D3 and D4 are the diodes that are on. And then we also discussed that we can get the same functionality using a different topology as appears over here, using a transformer that has a sensor tap on the secondary side. Pretty much everything is the same. We are only using 2 diodes. But in terms of voltage waveforms, we are doing the same job. Again, the output voltage waveform is the absolute value of the input voltage waveform. Then we looked at a case that what if our load is, we made it a little complicated. What if the load is not a purely resistive load? What if there is some inductance also placed in series with the load? We looked at that. In this particular case, first we talked about the conductivity of the diodes. For instance, when the input voltage is positive, D1 and D2 are the diodes that are conducting. And when the input voltage is negative, D3 and D4 are the ones that are conducting. Now in this particular case, we looked at the Fourier series of the voltage that is appearing across the load and kind of broke it down to its component, looked at the steady state response of each individual component, then in the end we added all of the responses with each other, like what you do in a superposition kind of an approach. And the output current is going to be a waveform like basically this. You can see the output current waveform has a relatively substantial DC component, and that's actually what we would like to see. Once you find the output voltage, output current waveform, you can actually argue that this is the current for D1 and D2, this is the current for D3 and D4, and if you are interested in the input current, it's going to be like this. We also had a numerical example. We also had a MathCAD file and looked at, for instance, power factor, parameters like that using that MathCAD file, which is already, by the way, on Blackboard. And then the book goes on and assumes that what if there is a DC source also, or a relatively substantial stiff voltage source appearing on the output side. We did not cover this. And what we started discussing was, what if we have a capacitor placed in parallel with the resistor that we have as our load? So we're going to analyze this, and before I do so, I would like to remind you guys that if you go to Blackboard, where's Blackboard? I had a few requests to upload my kind of OneNote notes on Blackboard. So if you look at content and scroll down to class notes in OneNote, everything that I have covered so far is here. So if you're interested in opening them, I would not advise you to do so, because I may have erased something and wrote something else. So it's not really reflecting everything that I have covered in class. But in case you're interested in taking a look, here is actually all of it. And every few weeks, I just upload the new ones, or maybe after every session is over. And as I've already mentioned before, the entire notes that I have on these basic paper notes that I have, everything is actually here under this PDF file. The entire notes that I have, they're all scanned. All right, any questions? Okay, so we have no questions. So let's continue our discussion on a full wave rectifier with an RC load. Okay, so we're actually, let me make this a little larger. So this is where we are starting, a full wave rectifier with an RC load. The circuit diagram looks like something like this. We have our full bridge of diodes. Then there is a cap, a relatively large cap, placed in parallel with the load. And unfortunately, these diodes are not numbered in this figure, so let me number them. So let me call this one to be D1, and then D2, and D3, and D4. So now because we have a cap over here, there's kind of a competition of which diode is going to conduct, which one is not going to conduct. And basically what diodes do is they compare the input voltage value with the output voltage value. If the input voltage tends to get larger than the output voltage, then they start conducting. For instance, if you assume that this blue curve over here is the input voltage, it's a sinusoidal waveform. This is typically what you have available as your source. And also, as we have seen earlier, these kind of converters are taking the absolute value of our input voltage in some cases. So, so the negative input voltage may actually come in handy. So I'm actually plotting negative Vn as this dotted curve over here, just the same signal multiplied by -1, just in case I need that. So as it turns out, for instance, if you are interested in plotting the output voltage, let me plot it over the second cycle. Okay. This is the time that none of the diodes are on. And the reason is the output voltage is larger than the input voltage. So as you can see, the red curve that I have over there is larger than Vin and negative Vin. So it kind of makes sense that none of these diodes are going to be on. And I'm just going to label this to be mode 3. Okay. So in mode 3, all diodes are off. Okay, and the same thing happens actually here. So technically what's happening in this mode is we have a cap that has already kind of been pre-charged, and we're going to talk about how, and then it's just an RC kind of action going on. So basically what's happening is this cap is being charged through this capacitor, and there is an exponential term involved, and we are looking at the very initial part of that exponential term. And what happens here is the output voltage tends to get smaller than the negative of the input voltage, and that's actually when D3 and D4 are going to turn on. And when they are on, they're kind of clamping the input voltage and output voltage basically with each other. So basically, the input and output voltages will be the same. Let me try to redraw that. This wasn't very good. Okay. So we label this to be mode number 2, and that is when D3 and D4 are on. Okay. So when they are on, they are clamping negative V in to the V out, to the T output voltage. So that's actually what you will see over there. And same kind of mechanism happens over here, or maybe you can call it over here. It's mode number 1, and that is when the output voltage tends to get smaller than the input voltage itself, and that's actually when D1 and D2 are conducting. Okay, so no mode number 1. Are on. So we have seen this mechanism before. It's the only difference is over here, not only the input voltage contributes to the output voltage, also the negative of input voltage sometimes contributes to the output voltage, and that is mode number 2. So technically, if you eliminate mode number 2, you will come back to that half wave rectifier with an RC load that we had earlier, like last week. All right, to highlight these time instances, I will label, okay, so this would be our output voltage again. I will label this to be alpha, and this angle to be basically theta. And since everything is symmetric, then over here I have pi plus alpha. And again, and so on and so forth, okay? So you kind of have the duration of each mode by marking alpha, and by the way, this is omega t. Okay. So if you want to have an expression for the output voltage, there are two segments in the output voltage. In one segment, which is like in mode 3, this is, by the way, mode 3 as well, and this is mode 3, and this is mode 3. In mode 3, we just have an exponential term describing the output voltage, and in modes 1 and 2, we are actually looking at the input voltage, which is exactly identical to the output voltage. So if you want to have a mathematical description for the output voltage, it would look like something like this. Sometimes the output voltage is the same as the absolute value of the input voltage, and that is during modes 1 and 2. And sometimes it's following some sort of an exponential pattern, and that is during mode 3. Okay, so once we have theta and alpha figured out, then we can actually exactly describe our output voltage waveform. All right, so in this expression, what is theta? How can we find theta? We have done the math a little bit before, but we are not going to repeat that. So theta is the answer to this equation. So theta is the inverse tangent of negative omega RC, and please don't use this equation when you are using a calculator. Instead, use this one. This gives you a better actually answer. So please remember, theta is more than 90 degrees, a little bit more than 90 degrees, like 91 degrees or 90.5 degrees. So if you have omega, which is the radian per second frequency of your system, angular frequency of your system, R is the value of your load, and C is the value of capacitor that you're using. If you use this expression, you can find theta, which is the end point for modes 2 and 3. Okay. Now what about alpha? How are we going to find alpha? Alpha would be the solution to this equation. So technically what we are doing is, drop the pen here. Okay. If you look at the output voltage waveform, you can argue that at omega t equals pi plus alpha, which is basically this point, what happens is the input voltage and output voltages are the same. So if I write my input voltage, which is negative Vm sine of pi plus alpha, is the same as the output voltage, which is Vm sine of theta times e to the power of negative pi plus alpha minus theta divided by omega RC. Okay, so we know that at omega t equals pi plus alpha, this happens. Actually, mode 2 and mode 3 are kind of crossing each other. So on one side of the equation, I have the expression for mode 2. On the other side, I have an equation for mode 3, and I'm trying to assume that they are the same. So if you solve this equation, you can actually find alpha. And as it turns out, there is not an easy way of finding alpha. Should be basically some struggle a little bit. And by the way, this negative sign is the right one over here, and please disregard this positive sign over here. All right. So alpha is the solution to this expression. And as it turns out, if you compare the alpha that you find here, compare it with the alpha that you were finding for a full wave, for a half wave rectifier, if all the parameters are the same, alpha for a full wave is larger than alpha for a half wave. It doesn't really matter, but just an interesting thing to note. All right. So now the next question is, let's talk about the ripple in the output voltage. For instance, what is the peak-to-peak ripple in the output voltage? So what do we mean by ripple? That means how much we are deviating from an ideal DC waveform. So if I look at the peak value of my output voltage, let me use, I don't know, let's use black again. If I measure my output voltage when it is at its maximum value, and also measure it when it is at its minimum value, and actually compare the difference, I would call this is the peak-to-peak ripple in the output voltage. So there's an expression for that, and the expression is kind of complicated because we need a solution for alpha, and in case you don't have alpha, there is an approximation involved, and the approximation is if omega RC, which are the parameters in the system, as a designer, you basically have control over the value of the cap that you want to use. If omega RC is much larger than pi, then we can use that approximation and say delta V out is almost the same or equal, or can be described as Vm, which is the peak value of the output voltage, divided by 2, divided by the frequency of the line, divided by the value of the load, divided by the value of the capacitor. So basically, you can use this approximation if this condition holds. And usually it does, so you don't really have to worry about what if it is being violated. And we have a numerical example over here. So for instance, so we have a full wave rectifier with an RC load, and the input voltage in terms of RMS terms is 120 volts, the frequency is 60 hertz, and the load is variable between 5 to 10 ohms. And we are trying to determine C so that delta V out is actually, in worst case scenario, is actually only 1% of the DC output. Okay. So what I'm doing here is the equation that I'm using over here is, a rearranged version of this guy over here. Okay. So I just took C on the left side, which I'm trying to find, and delta V out on the right side, appearing in the denominator. Okay. So if I choose C like this, using this expression, I'm guaranteed to have everything, but maybe I want to go a little bit beyond that and say, okay, what if I choose a little bit of a larger C, then I'm definitely guaranteed to have that. And please remember, Vm, which is the peak value of your input voltage, in this example is fixed, so you don't have to worry about that. Frequency is almost fixed. Delta V out is determined by the customer, which is like 1% thing, and that's relatively fixed. But R is the variable one over here. As you can see, R is changing from 5 to 10 ohms. So the question is which value of R you should be using. So in expressions like this, you got to make sure you maximize this, and then make sure C is even larger than that maximum value. In order to maximize this expression, I should use the minimum value of my R to maximize that expression. Please don't use, in this particular case, please don't use the maximum value of R. Okay. So again, I'm going to repeat that. You have to maximize this expression given the variability in the system, in this case, variability in the value of R, and then make sure C is even larger than that maximum that may happen. So because R happens in the denominator, I have to use R min to maximize that entire expression. So that's what we are using. All right. The only thing that we don't, we actually have pretty much everything, I guess. The only trick is when it comes to substituting the numerical value for Vm. Please remember the RMS value is given. A lot of students forget and get confused about the RMS and peak value. If the RMS value is given, multiplied by the square root of 2 to get the peak value, and then the rest are this here. 2 is here, frequency 60 hertz. Load minimum value 5 ohms, and basically delta V out, which is this expression, which is the 1% of the DC. The only approximation that I'm doing over here is I don't have the DC value of the output voltage, but I'm pretty much sure this DC value is very close to the peak value. So instead of the DC value, I'm actually using the peak value because there is only less than 1% difference between them. So I kind of making another approximation here. So instead of the average value of the output voltage, I'm using the peak value of the output voltage, but no problem, they are very, very close to each other. So as it turns out, C should be larger than like 0.167 farads, so it's a relatively large cap. And then if you go to the market, you are going to realize that you cannot really find a C that exactly matches this value. So you have to go with the larger value, the first larger capacitor that is available to you, like 0.17, for instance, farad or something like that. So please remember, later on we are going to actually look at DC to DC converters, and over there the switching frequency is relatively hard, like 100 kilohertz, and the caps that you need are relatively small. But over here your frequency is 60 hertz, which is the frequency of the line, and as you can see your cap would be a relatively large capacitor. It's very bulky and huge. All right, any questions? All right, so if you want to continue on drawing a bunch of waveforms, for instance, you may want to say, okay, I'm interested in plotting the current waveform of the diodes. As it turns out, D1 and D2 are on here, and D3 and D4 are on over here. For instance, if I'm interested in plotting ID1, which is the same as ID2, I only have to focus on mode number 1. And it's going to be a current waveform like this. How did I get this waveform? I know I have an expression for my output voltage. I have a very accurate expression for my output voltage. If I divide this by the value of R, I will get IR. If I get the derivative of this and multiply it by C, I will get the current of the cap. And once you add them by each other, it's going to be this current. And in mode number 1, this current and ID1 and ID2 are the same. So if you are curious about where is this form factor coming from, that's actually coming from, somebody has already done this, so I'm not going to repeat that. And again, we have to wait for another mode number 1 for D1 and D2 to conduct. So it's going to be here. So your dot current is like this. All right. Now when it comes to, for instance, I don't know, D3 and D4, it's almost the same waveform, only shifted 180 degrees to cover mode number 2. So when it comes to ID3, which is the same as ID4, D3 and D4, if you look at the modes, they are only on during mode number 2. And basically mode number 2 is here. So I'm going to actually follow mode number 2 to plot the diode currents. And as it turns out, it looks like something like this, for instance. All right, something like this. So it's pretty much the same, only similar to the D1 and D2 currents, only 180 degrees shifted. Now, if you are curious, for instance, curious about what about the input current waveform? Okay, we have D1 current, we have D3 current. So all you have to do is just basically apply KCL over here. So this is the input current, this is ID1, this is ID3. So applying KCL at that node, you would conclude that In is ID1 minus ID3. I already have ID1, I already have ID3, I just have to subtract them from each other. So technically you have to subtract these two waveforms that we have on the board. And if you do so, let me just get some space. Okay, so let's say you're trying to plot I in. So there is a contribution in I in because of ID1, which was here. And there's a contribution in I in because of ID3 with a negative, basically, sign over here. And this goes on. All right, something like this. So you can see it's kind of an AC signal. It's not a sinusoidal signal. It's an AC signal. It's in terms of frequency, the same happens to have the same frequency as the output voltage, but it doesn't provide a very good power factor, because ideally you would like to see an input current that is sinusoidal. I have a MathGet file which is already uploaded on Blackboard. Let me open it. The file name is full bridge rectifier with RC load. It's under those files on the, on MathGet. So I'm just trying to graphically show you what happens to the waveform, and also here it's easy for me to change a parameter and see changing that particular parameter what effect that change would have. So here we have a full bridge rectifier. The load is an RC load. The input voltage in terms of peak is 110 times the square root of 2. Let me see if I can make it a little larger. $125. Okay. The frequency is 60 hertz. Cap is 1 millifarad, relatively large cap. Load resistance is 20 ohms. Omega in terms of angular frequency is 2 pi times f, and theta, which was the when two of these modes collide, was, according to that equation, was pi minus inverse tangent of omega RC. And as I said, theta is usually close to 90 degrees. Over here it happens to be 97 degrees. Then I have to find alpha, and what you see over here is basically a MathGet programming to find alpha, and alpha turns out to be 47 degrees. Again, remember, alpha is between 0 and 90 degrees, close to 90 degrees in this case, because the parameters are not well chosen. For instance, the output cap is relatively small. You can see alpha turns out to be a small angle. All right. So this large expression over here is nothing but what we had earlier, which was a mathematical description for the output voltage, which is this expression over here is basically. So that's a MathGet version of this basically expression. And again, the diode current is, again, I didn't actually develop a model, an equation for that, but I explained how. You divide it by R, you take derivative of it, multiply it by C, then add those two terms with each other. As you can see, I have a division by R, I have a multiplication by C, and the derivation has been happening because sine turned into cosine. So this is a description for my D1 current. And also I'm looking at a bunch of terms. For instance, the average value of the output voltage. I have an accurate expression for my output voltage. I can just integrate it over one period and then find the average value, and turns out to be 136 volts. And the average value of the output current, and please remember, output current is defined as the current of the resistor, not this current over here, the current of the resistor. So the output current would be the average value of the output voltage over the value of the resistance, so that would be 6.8 amperes. All right, so let's look at some of these waveforms. Let me see why it looks like this. Okay, so the solid blue line is what your output voltage would look like. I'm just plotting it for like 1.5 times pi in terms of omega t. I'm not even plotting it for one period. This angle over here is your alpha when your diode starts conducting, and this is actually your theta when the diode stops conducting, and alpha was 47 degrees. So if this is 0 degrees and this is 90 degrees, and this was a little bit beyond 90 degrees. All right, at the same time, this dashed line is the average value of the output voltage. As you can see, it kind of makes sense, because if I look at this little positive area over here, kind of cancels out this negative area over here, so I can claim that this dotted line is the average value. And also I have a very kind of a low dashed line over here, which is the average value of the output current. The reason that I'm plotting this over here is to show that the diode has to conduct almost a peak current of 50 amps, but on average we are only looking at 6.8 amperes of output current, and that's actually one of the problems associated with this topology. Your diodes, in terms of the current that they have to conduct, are stressed a lot. And then later I am, for instance, looking at the RMS value of the diode current, which is 14 amps. Again, to find the RMS value, just go with the original definition, multiply the signal by itself, and take the average of the signal over one period, and then get the square root of the whole thing. And I can also find the average either input power or output power. Over here I'm looking at, on the input side, I multiply the diode current by the input voltage for half of the cycle, because that's actually when power transfer is happening. From here to here you have power being transferred from source to load. So that's what I'm using to find the average value of the power, and it's about 950 watts or something like that. And in terms of power factor, I find the RMS value of the power, and then on the other side I find the I find the average value of the power, which I found here. So I'm using it down here. And then on the other side you look at the apparent value of the power, which was the RMS value of the input voltage times the RMS value of the input current. This is the RMS value of the input voltage, and this one over here is the RMS value of the input current. But please remember, what I'm doing over here is I'm analyzing the system in only half of my cycle. That's why, for instance, D3 and D4 do not even appear over here. But if you be careful about it, your numbers are going to be correct. And power factor turns out to be only 58%, which is not a very good power factor, okay? So it's kind of a trade-off over here. The power factor is relatively bad, and the reason for that is the diode current looks very awful, but at the same time your output voltage is relatively DC, and this solid blue line is almost DC. Now you can see what happens if you change some of the parameters. For instance, I can say I want to make my cap very, very, very large. So for instance, let's purchase a cap that is 10 times larger than the cap that we have already chosen. If I could do that, hold on, let me move this a little bit. Okay. Let's use a cap that is 10 times larger. Okay, see what happens. If I use a larger cap, omega RC, because C has grown 10 times larger, omega RC is growing 10 times larger. So I would expect alpha to get closer to 90 degrees. Let me get a better shot. So I would expect this guy to move towards 90 degrees, and theta also move backwards toward 90 degrees. And you can see they do that. And at the same time, my output voltage is even closer to a DC waveform. You can even identify the difference between the solid blue line over here, which is my real output voltage, and there is a little bit of a dashed line over here, which is the average value of the output voltage. So in terms of my output voltage, everything gets better if I use a larger cap. But at the same time, if you look at the diode and the current of the diode, which is this green line, you can see the stress on this diode has even further increased. Now the peak current of the diode is somewhere around like 160 amps, okay? But the power hasn't changed much. And if you look at the power factor, it has got even worse. It's got like 36% instead of being an ideal case of like 100%. And why is that? Because the diode is even, in terms of conduction, is even conducting in a shorter period of time. Now, on the other side, you can argue that, okay, so let's go back to the previous case of original design. You can say that my load is okay with an output voltage that is not absolutely DC. You can even further disturb this, and the compensation, the trade-off would be improving the power factor. So let me use a cap that is even 10 times smaller than my original design. So in this case, omega RC is getting smaller. So I would expect alpha to get closer to 0. That is, alpha has to move further to 0, and theta to move further after beyond 90 degrees. And that's actually, okay, no, wait a minute. This is too small. Let's make it a little larger. Okay, I don't know if you can tell the difference. Let me try it again. Okay, originally my cap was 1 milli. Okay. So this is what I had. Now I change it to a smaller cap. So let's say 0.4. Okay, you can see that in terms of the DC component in your output voltage, you're getting actually worse. You have a lot of ripple now, but diodes are actually doing better. The diodes are conducting for a longer period of time. Modes 1 and 3 have been extended, and the peak value of the diode current has actually reduced to maybe 25. And if you look at the power factor in this case, it has improved a little bit, like 0.668. Now, please remember, even if you eliminate the cap, you cannot achieve, you can actually achieve a 100% power factor, but my simulation over here does not support that, unfortunately. So you cannot just eliminate this cap or place it to be very, very zero and then get something. So, and this is a little bit of a crippled. All right, so this file is already on Blackboard. If you want to play around with it, do that. The only thing that I would like to warn you is if your input voltage turns out to get, if your output voltage, which is the solid blue line, turns out to be negative, that means you are in the wrong operating region. So please be aware of that, okay? It's not guaranteed that any number that you plug in is going to give you the right numbers, the right answer. All right. Any questions so far? All right. So what the book does next is it looks at controlled full wave rectifiers. Okay, by controlling we mean we have replaced the diodes with SCRs, and SCRs have gates, and we can control those gates to turn on and off, or turn on basically, and that's why they are called controlled rectifiers. So as you can see, this topology over here, it has 4 SCRs, S1, 2, and 3, and 4. S stands for SCR. And then we want to actually analyze that. As it turns out, these topologies gives us a little bit of flexibility in terms of controlling the DC component of the output voltage. So if you have an application in which you would like to control the DC voltage over here, for instance, you are trying to build a power supply, okay? And the user of the power supply should be turning a knob and controlling the output voltage level, something like that. That's what we would use. All right. So going back to my notes, we are over here basically. Controlled full wave rectifiers, and that's actually on page 8. And this is NF, obviously. Okay. The first case, which is the easiest case we always analyze, is what if we have a resistive load? Everything gets very, very easy. All right, so let's do that. All right, so let me go back to these waveforms and kind of analyze the system. All right, so remember, if we do not trigger any of these, SCRs, nothing is going to happen because they are never going to be turned on, and technically the load is totally isolated from the source, and the output voltage is 0. Okay, so that means that it's like as if you haven't turned the device on. Well, obviously that's not what we want to happen, and the way we trigger these guys is, all right, so technically in order to turn these guys on, you need a triggering signal. So let me call this the current of gate number 1 for SCR number 1. So there's like, if you want to turn this device on, you send an impulse of current to the gate of this device. And as it turns out, these two currents are always pretty much the same, or gate number 1 and gate number 2 are always triggered at the same time. And with 180 degrees of phase shift, we have triggering happening for gate number 3 and gate number 4. Okay. So if you look at that half wave rectifier, control rectifier that we analyzed, when the input voltage is positive, it is a good time to trigger SCR1 and SCR2. So this would be IG1 and IG2. We write it here. Okay. Why is that? Because right before that, SCR1 and SCR2 are forward bias, so they are ready to be turned on, and you just trigger them and they turn on. And when the input voltage is negative, it's a good time to trigger S3 and S4, because in that case they are forward bias. So if you are trying to trigger S3 and S4, you would trigger them somewhere around here. Okay? Okay. So when the input voltage is positive, we have the opportunity to turn S1 and S2 on because they are forward biased. When the input voltage is negative, we have the opportunity to turn S3 and S4 on because now they are forward biased. And we just label this angle to be alpha, which would be the triggering angle, something like that. And because if you want to do because we would like to do everything symmetric, this would be pi plus alpha. Okay. So let's have this in mind. And for instance, plot the output voltage waveform. Okay. All right. I wish I could. I made this a little smaller, but anyway, let's try plotting the output voltage. So before we have triggered the devices, they are all off. Okay, if they are all off, that means we have no current going here, no current going here, therefore no current going here. That means the output current is 0, therefore the output voltage is 0. All right, so let me delete this. Okay. So before we have triggered anything, everything is practically 0. So here I'm trying to plot the output voltage. Okay. Now, if you write KVL and stuff like that, you would realize that S1 and S2 are forward bias, so they are ready to be triggered. And if we trigger them, they are going to operate like a short circuit. So as soon as we trigger them, what happens is you have a short circuit here and you have a short circuit here. So technically, you're looking at this loop. All right. If you write KVL around this loop, you would realize that the input voltage and the output voltage are basically the same. Let me just so after they are triggered, the output voltage just follows the input voltage. All right. The question is, how long is it going to do that? First of all, remember, we cannot turn SCRs off. We can just turn them on, and they make their own decision of turning off, and that is when their current tends to get to 0. So as it turns out here, the voltage returns back to 0, and I'm talking about a purely resistive load. That means also the current is coming back to 0, and that's actually when SCR1 and SCR2 are going to turn off. So please remember, not only this is the V out, this is also R times I out. Okay? Or let me use lowercase I. All right? So if you want to mark these events, obviously this is alpha, this is pi, and this is omega t. So over here you have SCR1 and SCR2 turn on. Okay? And at omega t equals pi, you have SCR1 turn off. Okay. So they turn off. So beyond this point, again, everything is off because we haven't triggered 3 and 4 yet. So everything is off. All the currents are 0. The output current is 0. Therefore, the output voltage is 0. And this continues until the next triggering arrives. All right. So at this point, we are triggering SCRs 3 and 4. So technically you have a short circuit path here and you have a short circuit path over here. So technically you're looking at this loop of, okay, let me see. Kind of like, it's like a twisted kind of an 8. So if you write KVL around the loop, you're going to realize that V out is the negative of Vn. And the dotted line is already the negative of Vn, so I have to just follow that. Okay, so something like this. So again, these SCRs are going to continue their conduction until their current turns to get negative, and that's actually happening at omega t equals to pi. So here you would say SCR 3 and SCR 4 turn off. And here is when SCR 3 and SCR 4 are turned on. All right, and this is one cycle. Then you just keep doing this, keep repeating the cycle. So again, you trigger G1 and G2 here, and again G3 and G4 here. So you just keep doing that. All right, so you can see that I'm kind of chopping off part of the output voltage that I could have, and that gives me a control, basically a little bit of a control, which would be actually the angle of alpha. So if you compare this with an uncontrolled full wave rectifier, which we had, for instance, here, you can see here the output voltage is just the absolute value of the input voltage, versus if you do that in a controlled way, the output voltage is sometimes 0 and it is sometimes equal to the absolute value of the input voltage. Okay. So, and as I said, this is the output voltage waveform as well as the output current waveform, because we only have a purely resistive load. And if you are interested in plotting the input current, or before that, let me just mark this peak value to be Vm. All right. And if you want to plot the input current waveform, so in the well, obviously in the very before alpha arrives. Okay, we use another color. Let me use red. Before alpha arrives, nothing is happening. Everything is 0. All currents are 0. So I'm pretty much guaranteed this would be 0. This would be 0. All right. But after I trigger alpha, for instance, at omega t equals to alpha, the output current is non-zero now, and basically so is the input current. So the input current and output current are the same, so I'm just going to plot it. All right. So this would be here. So first of all, I'm plotting I in. Here I in is the same as I out, and this peak would be Vm over R. Okay, and for the second basically half of the cycle, we kind of have the same behavior. I'm sorry, this is not the right one. You have a behavior like that. Why is that? Because in this phase, I in is the opposite of I out. So if I out is positive, I in is negative. So we are looking at a waveform like this. All right, something like this. It's almost sinusoidal, but part of it has been chopped out because of this SCR action that we have got going over here, basically. All right. Any questions? So this could be a very good typical quiz question or an exam question that we give you a rectifier and then you have to, for instance, plot a bunch of waveforms. Why? Because I'm assuming that you know how these waveforms, how the operating, you know about the operating modes of the converter, and you're able to analyze it. All right. So once we figure out what the waveforms look like, what we got to do is, for instance, look at this waveform over here. Which is the output voltage waveform, and try to find its average value. Again, if you look at it, this is a periodic signal. It doesn't matter if you assume that the period is from 0 to 2 pi over here, or 0 to pi. I mean, we have like twice the line frequency symmetry in the system. So you can actually look at the average value of the signal and argue that this would be, oops. Okay, I'm running out of space. I just wrote d omega t down there, but they're all in the same line. Okay, so what happened here? First of all, because of the symmetry in the waveform, I'm just doing the integration for pi. Omega t equals from 0 to pi. Then because my signal is 0, I'm not even doing 0, starting at 0. I'm actually starting at alpha. Okay, so this turns out to be, I'm sorry, we are looking at the absolute value of the input voltage. I'm sorry, the average value of the input voltage. So V out on average is Vm over pi 1 plus cosine of alpha. All right. So this actually hints that if you change alpha, you can actually control the average value of your output voltage. So if alpha is 0, we are back to the original case of an uncontrolled rectifier. So the absolute value, the average value of your output voltage would be 2 over pi times Vm. If alpha is like 90 degrees, you can argue it's only Vm over pi. If alpha is 180 degrees, you almost get 0 output voltage. So you can actually change the average value of your output voltage. And obviously, the average value of the output current is the same as the average value of the output voltage over R in this case, because my load is just a purely resistive load. All right. Now, if you're interested in finding the RMS value of these signals, for instance, the I out RMS or I in RMS, first of all, if you compare I out and I in, you would argue, you can actually conclude that I out is the absolute value of I in. If you compare this red curve that we have over here as I in and this kind of black curve that we have over here as I out, you can see I out is always positive, and it's like the absolute value of the input current. So because it's a rectifier basically. So if I have an original signal and then take the absolute value of that signal, the RMS value of the two signals should be the same. So that's why in my notes I have this equation. Okay, maybe I should rewrite it over here. Just rewrite it down here. I in terms of RMS values is the same as I out in terms of RMS values, and that would be, I'm just writing the answer, Vm over R 1 over 2 minus alpha over 2 pi plus something like this. kind of similar to an equation that we had earlier. There's like a square root of 2 involved. The difference is that. And please remember, if you are trying to numerically find the RMS values for alpha, you should always plug the RMS values. I'm sorry, the radian values, not in degrees. So this alpha in radians, not in degrees. All right. So this is an expression in case you want to find the RMS value of the input current or the output current. Why? For instance, because you're trying to find the output power or the input power and you need the RMS values. All right. So this is pretty much what we go as far as these rectifiers are, this controlled full wave rectifier is concerned. This is the expression that I just wrote up there. I in RMS is the same as I out RMS, and the results are, I already wrote it up there. Now, what the book does, it actually covers some special cases of this, like what if instead of having just a purely resistive load, having also an inductor placed in series with the load. So we are actually looking at a schematic like this now. So this inductor over here is the extra component that we are considering. So from the experience that we have had so far, you can argue that inductors tend to make the currents a little bit sluggish, or a little bit closer to a DC form. And there are two cases involved over here. One case is the inductor is relatively small, or alpha, the firing angle, is relatively large. So the current of the output basically side, this current over here, is kind of discontinuous, meaning that it starts from 0, goes somewhere up, then comes back to 0, and then remains there for the next half of the cycle to repeat. And the other case is if the inductor is relatively large or alpha is relatively small, what happens is the output current is just going to be continuous. Just continuously you are going to have some current flowing through here. So the book has differentiated these two from each other. So I can, for instance, look at the first one. Let's look at the first one. So basically what happens is, if this is the input voltage, and this is the negative of the input voltage, okay? And this is the triggering angle. So I just call this IG1 and 2. And then 3 and 4. Okay? So the triggering doesn't really make a difference. It doesn't really change from the previous case. Now what happens is, so let's call this alpha and pi plus alpha. Before alpha arrives, everything is 0. We haven't even triggered anything, so we are 0. I'm trying to plot I out. All right, the current is 0. Then we trigger the system, and what happens is you're actually applying your input voltage across this resistor placed in series with this inductor. There's a differential equation involved. You have to solve that differential equation, and if you plot the current is going to look like this. Something like this. And here I'm actually looking at a case that the current is discontinuous, meaning that before the next triggering time arrives here, which is pi plus alpha, the output current returns back to zero. This is an indication that, for instance, your inductor is very small, okay, or alpha is relatively large. So when the inductor returns, the inductor current or the output current, technically they are the same. When it returns back to zero, that means everything is zero now. Those SCRs that we triggered at omega t equals to alpha are not conducting anymore because the current has returned back to zero. So here we got nothing going on. Everything is zero again. All right. Now, pi plus alpha arrives. I'm triggering SCR 3 and 4. And I'm applying negative of the input voltage across the load, and I will have the exact same action going on. All right, until 2 pi plus alpha arrives. And the same. Okay. So this would be our waveform for the output current. As you can see, the output current is discontinuous, meaning that sometimes it remains at zero and does nothing basically. And this angle is labeled to be beta. And there is symmetry in the system, and this would be pi plus beta. Okay? So beta is like, I don't know, a little bit larger than 180 degrees or so. Okay? So technically you can look at some modes of operation and say, okay. So this is page 9. At omega t equals alpha, SCR1 and SCR2 are triggered. That's actually what we are indicating by this guy over here. Okay? Before that, nothing was going on. After that, we have SCR1 and 2 on, and SCRs 3 and 4 were off because we did not even trigger them, okay? And basically we are applying, okay, if you are interested in one more waveform, which would be Vx, hold on. All right, well, obviously this is our output voltage. Okay, in my notes it appears to be Vx somehow, I don't know why. But anyway, if you're interested in plotting Vx, as long as these SCRs are on, 1 and 2, Vx and Vn are the same, so they are on from omega t larger than alpha and smaller than beta. So from here to here, I have SCRs 1 and 2 on. So if I'm interested in plotting V out, which is the same as Vx, depending on what notation you're looking at, it is following the input voltage. All right. Then in this mode, nothing is going on. Everything is zero. So V out is also zero. Okay. Then beyond this point, so this is pi plus alpha. Beyond this point, SCRs 3 and 4 have been turned on. So V out is, or Vx are following negative of Vn. And the dotted line is the negative of Vn. So I'm just going to follow that. So we have a waveform like this. As our output voltage, okay? So this would be our V out or Vx, depending on what notation you're looking at. So we would like to look at this in case you're interested in finding the average value of the output voltage. You technically have to take the average value of the signal. So if I want to basically complete it, this would be alpha, this would be beta, this is pi plus alpha, and the rest you can figure it out basically. So over from here to here, 1 and 2 on, oops, and then from here to here, 3 and 4 on. And the rest, everything is 0, they're all off. So this is actually what I have over here at omega t greater than theta and smaller than beta, V out and V in are the same. At omega t equals to beta, these two currents, the current of the output returns back to 0, so S1 and S3 turn off. Then beyond that, all switches are off until the next half of the cycle arrives, and then we trigger the switches, and then V out is the negative of a V in. All right. So you can see finding the output voltage is a little bit tricky here. The output voltage sometimes gets negative, and why is that? Because this SCR continues the conduction even though the input voltage has turned negative, and that's why we are still following the input voltage here. We are following the input voltage even though it's negative, because the SCR hasn't turned off yet, because its current has not returned back to 0 yet. We are actually applying some negative voltage across our output voltage, and then they turn off. Then all of a sudden current jumps back to 0 because nothing is on, all the currents are 0, therefore the output current is 0. All right. Now, the question is, okay, the other alternative would be either the inductor is large or alpha is very small, meaning that before this current has the opportunity to return back to 0, before it has the opportunity to return back to 0, we do the next triggering thing, okay? So that means, for instance, L is large or alpha is very small. So what happens there is we are not going to have any 0 current modes, because before current has the opportunity to get back to 0, technically we have triggered the other two devices. Okay, so let's take a look at that one. Let's see if I have waveforms for this. All right, let me just increase. All right, so let me just copy and paste a bunch of waveforms. All right. So these waveforms over here, these are the discontinuous phase. Discontinuous case. And what I'm about to draw is the continuous case. Okay. And we will see later, we are going to see under what circumstances the continuous case happens, under what circumstances the discontinuous case happens. So far, let's say this solid blue line is the input voltage, this dotted line is the negative of the input voltage. And the triggering hasn't changed, so we are still triggering the devices here. So we are triggering 1 and 2 here, also here, and then we trigger 3 and 4 here and here. All right. But L is relatively large, and the inductor current does not have a chance to return back to 0. So basically, if I'm trying to plot I out or the inductor current, they are basically the same. What happens is when we trigger the devices on, because previously they were forward biased, they turn on, and they actually have a, like it starts from here. They start conducting, and there is some basically action going on. There is a differential equation involved to have to solve and find the answer. And then, so this is alpha, and this is pi plus alpha. Then pi plus alpha arrives, and the current has not even returned back to 0 yet. Pi plus alpha arrives, and we are triggering 3 and 4 on. They were previously forward biased, so they have the eligibility to conduct, and they force 1 and 2 to turn off. So another action going on like this. So something like this. So this would be your output current. So over here, 1 and 2 on. Over here, 3 and 4 on. And this just periodically happens. The current does not have a chance to return back to 0. For instance, because L is large, we are in the continuous mode of operation. So this would be your basically output current, almost DC. Now, if you are interested in, for instance, plotting your, for instance, output voltage, which is labeled as Vx or Vout over here, this output voltage over here, let me plot this. The whole trick is when 1 and 2 are on, the output voltage is the same as the input voltage. However, when 3 and 4 are on, the output voltage is negative of the input voltage. So, all right. So in this time interval, as I just mentioned, 1 and 2 are on. Therefore, the output voltage is the same as the input voltage. Then beyond that, 3 and 4 are on. Therefore, the output voltage is the negative of the input voltage. So I have to follow it from the negative dotted line. All right? Okay? And then again here, 1 and 2 are on, so the output voltage is the same as the input voltage. Assuming that the blue curve is the input voltage, I'm just going to follow that. And then beyond that is the negative of the input voltage. So here, this would be your output voltage waveform. All right, so this would be your Vout. Or Vx. Okay. So those 0 periods are kind of eliminated. Before, remember, it's almost the same waveform that we had earlier. The only difference is here we had a case that sometimes our output voltage was 0. And that was when all of the switches were off. Over here, there is no mode during which all the switches are off. Either 1 and 2 are on, or 3 and 4 are on. There's no other mode. So that's actually what your output voltage looks like. There's lots of other waveforms. I don't really want to get into the details of them. The only thing that we have to care about is under what circumstances the continuous mode happens, under what circumstances the discontinuous mode happens. And there is an equation for that. So if you do some math and, for instance, argue about, okay, alpha should arrive before beta arrives, or beta should arrive before alpha arrives, you are going to end up, with this expression. If alpha is smaller than the inverse tangent of L omega over R, then the continuous current happens. Otherwise, the discontinuous case is going to happen. So if you're analyzing a bunch of numbers are provided to you, first thing that you have to check is, are we in the continuous or discontinuous mode using this expression, and then go ahead and make those basically waveforms that are associated with the particular mode that you are analyzing. Okay. I'm going to stop here. Please take a look at the notes. Please take a look at the book. There is more descriptions. There is lots of equations involved. We are kind of trying to just touch these because I don't really want to spend a lot of time on these, whereas we have more important stuff to cover, and as long as the DC to DC converters are concerned. So I'll see you guys on Thursday.